In this video, we shall take a closer look at the concept of uniform circular motion. When an object moves in a circular trajectory at a constant speed, let's assume the direction of motion is counterclockwise. The radius of that trajectory is r, and the speed is always constant, namely v meter per second. Note, I stress the word speed, not velocity. Let's assume the speed is 10 meter per second. Note that although the speed is always 10 meter per second, the direction of that velocity is not the same all the time. It changes like that. What that means is there should be an acceleration. After all, acceleration is defined as the final velocity minus the initial velocity over a certain time interval. So as long as this number is different from that number, there should be an acceleration. Such an acceleration that corresponds to uniform circular motion of an object is known as the centripetal acceleration. The magnitude of the centripetal acceleration, for example, in this case, is equivalent to that constant speed squared over the radius of that trajectory. As with any other acceleration, the unit for centripetal acceleration is meter per second squared. Note that in this expression we have just written its magnitude. How do we determine its direction? After all, centripetal acceleration is a form of acceleration and therefore is a vector quantity. To answer this question, let's pick 2 points. Let's pick this point as the initial point and that point as the final point, and analyze the direction of the velocities. Let's redraw these 2 positions in this diagram. The first position is that, the second position is that. So when the object is here, its velocity is, let's say, vi, I for initial, and when the object is there, the velocity there is vf as for final. We note the speed or the magnitude of these velocities are the same. The time it takes to go from this position to that position is, let's say, delta t. We want to address the direction of the acceleration because after all the velocity changes. As we have seen before, the acceleration, in this case it's a centripetal acceleration, is given by the final velocity minus the initial velocity over delta t, where delta t is the time interval. We need to figure out the direction of that vector. We note that vf minus vi is after all vf plus minus vi. So we are taking difference of 2 vectors. So how does a vector vf plus minus vi look like? Vf is going in that direction. Vi is going in that direction as given here. So that means minus vi is going in an opposite direction. So that is the direction of that vector. In order to carry out this operation, to this vf we need to add minus vi, and minus vi is going in that direction. So that is minus vi. So when you sum vf and minus vi, we have to connect the tail of the first vector to the head of the second vector, and it goes like that. So the vector in yellow is this vector, which appears in the numerator for the expression for acceleration. So there we have it. As the object moves from the initial location to the final location, on average its acceleration is pointing towards the center like that. And that is the direction of that centripetal acceleration. So more accurately, at the instant the object is here, the direction of the acceleration is towards the center. Center means the center of that circular trajectory. Using the same analysis, we can show that when the object reaches, let's say here, the centripetal acceleration will go again towards the center in that manner. And when the object is, let's say, here, the centripetal acceleration is going like that, and so on and so forth. So there we have it. The centripetal acceleration of an object executing uniform circular motion has a magnitude of that constant speed squared over the radius of that trajectory, and its direction is quite simply towards the center of that circular trajectory. Since this is a circular motion, in addition to that tangential speed v that we have written there, there is another type of speed known as the angular speed, omega, that is related to that tangential speed, which is a form of linear speed. And this is how they are related. The tangential speed equals the radius of that trajectory times the angular speed. So that means the centripetal acceleration can be also written in terms of this omega as follows: r squared omega squared over r. So that means it's r omega squared. The unit for omega is radian per second because it is a angular speed. It is a measure of how much a radiant is covered per unit time as the object goes from here to there of that circular trajectory. A thing to note about this tangential speed and angular speed is as follows. If you have a couple of objects that is rotating about the same radial line, say like that, they would have different tangential speed in general. However, because they are sticking to the same radial line, both would have the same omega. So VR equals RR omega, where RR is the distance from the center of rotation to that object, and V, say yellow, equals R yellow times omega, where R yellow is the distance from the center of rotation to that yellow object. So you see, these two things are different. This remains the same. Let's look at this following problem. A red ball at radius 2 meters and a blue ball at radius 3 meters travel in uniform circular motion. They are on the same radial line. At one instant, the red ball has an acceleration of 2i hat plus 4j hat measured in the unit of meter per second squared. So this is indeed the centripetal acceleration because we're dealing with a uniform circular motion. Find the acceleration of the blue ball at that instant. So the process is depicted here. This is the center of that rotation. That distance is 2 meters and that distance is 3 meters. And they are going in a circular trajectory like that. As we have discussed earlier, both should have the same angular speed. We need to determine what that angular speed is. Now we know the centripetal acceleration of that red ball, it's given by that. We can determine the magnitude of that centripetal acceleration. We know the centripetal acceleration is given by this speed squared over radius. In terms of angular speed is omega squared r. For the red ball, the centripetal acceleration, the magnitude of the centripetal acceleration can be evaluated quite simply. It is from that expression 2 squared plus 4 squared square root, which is square root 20 meter per second squared. Substituting that information in this expression, we get square root 20 equals omega squared times the radius of the trajectory. For the red ball, the radius is 2 meters. So we can determine omega. And it turns out to be 1.49 5 radiant per second. This omega should also be the same omega for the blue ball. So using that information, since the omega for blue ball is also 1.495 radiant per second, we can determine the centripetal acceleration for that blue ball from that expression. It is quite simply 1.495 squared times the radius of the circular trajectory for the blue ball. In this case, it's 3. So you're gonna get 6.705 meter per second squared for the magnitude of the centripetal acceleration of the blue ball. What about its direction? Its direction will be towards the center of the trajectory. So just like the red ball, the direction of that centripetal acceleration of the blue ball is going like that. Now, can we write the direction in I hat j hat notation? Well, sure we can. From vectors, we know that the vector for the centripetal acceleration equals the magnitude of that centripetal acceleration, which we have determined, times the unit vector along the direction of that centripetal acceleration. So now all we have to do is to determine that unit vector along that radial line. Now we do know the unit vector for that direction must be the same unit vector for that direction, because that corresponds to the acceleration of the red ball. Since the acceleration of the red ball and the blue ball are the same, then all we need to figure out is to determine the unit vector along that direction. And that will be your u hat. So that means u hat equals the vector in question, in this case 2I hat plus 4j hat, over the magnitude of that vector, which is square root 20. So there we have it. The complete vector expression for the centripetal acceleration of the blue ball is given by 6.705 times 2I hat plus 4j hat over square root 20. And the unit is, of course, meter per second squared. Now let's simplify this. When you do the multiplication, you'll get a rather nice number, namely 3I hat plus 6j hat meter per second squared for the centripetal acceleration of the blue ball. And that solves the problem. As always, thank you for watching.